this lecture we are going to talk about some more things related to your one-dimensional finite element program. So till the last lecture we had essentially talked about the finite element method in the context of the one-dimensional problem, and we had essentially in a detailed way elaborated the various components that go into a one-dimensional code. So one has to put these components together, and once they are put together under the separate units called preprocessor, processor and post-processor, then I have my complete finite element program. Now the question is that what is it that we would like to see with our finite element program? Certain things that we should check for right in the beginning before we start using this program to ensure that it is doing what it is supposed to do. In a fleeting way, it was mentioned in the last lecture that we can do something called a patch test to check the one-dimensional program. Now there are various definitions of these patch tests given in various books. What we are going to do is something very simple. Okay, what is the basic idea? As I had mentioned, let us take this problem. So this is a bar again of length 1. Let EA be equal to 1, and currently I am applying no distributed forces. So in this case I know my differential equation is going to be corresponding to the deformation of the bar. It is going to be minus d to u dx squared is equal to f of x in the interval 0 to 1. Now f of x for us is 0. So this implies that for this case u of x, that is the exact solution, will be equal to ax plus b. Okay, and from our initial condition that we have applied here, the b would come out to be 0, but this is the representation. So my exact solution is actually a linear. This problem I am going to call as my problem 1. Okay. Similarly, what I would like to do is take problem 2. Here everything I keep the same as in problem 1, but now I apply a uniformly distributed load f of x equal to 1. When f of x is equal to 1, then if I look at this part on the right hand side, minus d to u dx squared is equal to 1. So my u of x here will come out to be minus x squared by 2 plus ax plus b. So here now if you see, my exact solution is a quadratic. So I should write it here. The exact solution is a linear, and here it is a quadratic. Okay, so let's take the third problem. I keep everything fixed as problems 1 and 2, But here I am applying an f of x which is a linear, which is given by f of x is equal to x. So, in this case I get minus u double prime is equal to x implies u of x is equal to minus x cubed by 6 plus c1x plus c2, where c1 and c2 will come from our boundary conditions. So, if you look at this solution, this is now a cubic. I could also create a fourth problem. Let me create it. Such that my f of x is a quadratic. If my f of x is quadratic, implies my u of x is going to be minus x to the power 4 by 12 plus c1x plus c2. So, it is going to be a fourth order. Now, our program is going to be designed to have orders of approximation 1, 2 and 3. So, if I solve these problems now using order of approximation 1, 2 and 3, okay. So, here what we are doing, we are constructing problems for which we know the exact solutions, and not only do we know the exact solutions are polynomials of some order. So, if I now try to solve this problem using the finite element method, using p equal to 1, 2, 3. So, for problem 1, all 3 should give me an exact solution. All 3 p equal to 1, 2, 3 should give me the exact solution. Why? Because my approximation is of order greater than or equal to 1, my exact solution is linear. So, I know from the completeness property of my approximating functions, I should be able to exactly represent the linear using these. Okay. So, now if I take problem 2, for p equal to 1, it is not exact, but for p equal to 2 and 3, it has to be exact. Okay. Problem 3, if I take, for problem 3, which is why is the previous problem exact? Again, because it is a quadratic polynomial, and the quadratic polynomial should be exactly represented by our approximations of order 2 and 3 because of the completeness. Problem 3, the exact solution is a cubic. So, here only for p equal to 3 it is exact. For p equal to 1 and 2, it is not going to be exact. Now, if I ask you the following question, what about problem 4? In problem 4, none of them are exact, because the exact solution now is a fourth order polynomial, and we are only able to approximate it using the linear, quadratic and the cubic. Now, how are we going to approximate? You can take, let us say, 3 elements in the domain. Okay. So, 3 elements of size 1 by 3, 1 by 3 and do the whole thing. But what we are going to see, in the cases when it is not exact, if I refine the mesh, Okay, that is, I add more and more points, I should get closer and closer to the exact solution of the problem. Now, for the polynomials, for the approximations for this problem, for this one, we said that the solution is exact. Okay. So, how do you check whether that exactness is coming out, okay, in terms of the degrees of freedom that you obtain? Now, if you plot, you may get the plots very close and you can conquer or kind of draw a conclusion that you have obtained the exact solution, but we should be able to check it numerically up to the machine precision that has been specified. So, how do we do? So, let us say that I have this 3 element mesh. Okay. So, what do? I take any element I k. For this element, I know this is going to be my x1 k, this is going to be my x2 k. Now, given the order of approximation p, I am going to have hk, which is equal to x2 k minus x1 k. This we have done many times over. We will take this h bar equal to hk divided by p. That is, we will take this smaller piece and now we are going to divide this guy into smaller pieces. That is, we are going to add these additional points, and you see how many points we are adding. Essentially, sorry, it will be hk by p minus 1. No, that's okay, hk by p, it's okay. Okay, we have taken these pieces and we will do this. Then what do we do further? So, we are going to do the following, that in the element I have the first node I am going to call x1k and I will give it another name x bar. Okay. Then the next node I am going to form, not node, a point, x2 bar k is equal to x1 bar k plus h bar. Then I will find the next point and so on. So, that way I am able to construct all the p plus 1 points in the element corresponding to a p order approximation. So, at these points now, once I have the exact solution expression, okay, so any generic point will have x1 plus I k bar is equal to x1 k bar plus I h bar. So, given these points, I am going to feed them to a routine which returns me the exact solution. Okay, at these points. Now, but we also know that if these are the exact solutions, how do I compare these point values with my finite element solution? By the construction of our shape functions, we know that these points also correspond to u1 of k, u2 of k, u3 of k, u4 of k, and so on. That is, these have the corresponding shape functions defined with respect to these points if I transform from the master to the physical and vice versa. So, we know that the degrees of freedom or the elements of the solution vector u that we have formed, they correspond to the value of the finite element solution at these points in the element. So, what are we going to check? So, we are going to check if u at x1 bar 1 plus I this thing is equal to, this is a question mark, u ig. Now, what is u ig? uig is equal to the ILDOFs for the element k 1 plus I going from 0 p plus 1. So, if I take all these i's, essentially it simply means that I go to the solution vector u, from there I extract this global entry of the solution vector, which corresponds to the ILDOFs k comma 1 plus I. So, it corresponds to u at this point. So, if all these values are 0, are equal up to the last decimal digit, that is up to essentially the error between the two is 10 to the power of minus 12 or less, then we say our nodal values are sufficiently accurate, or up to numerical precision it is exact. If these nodal values are exact, or the point values, that is the degrees of freedom, correspond to these point values, okay, and that they are equal to the exact solution, then we can say that at least for the cases where the exact solution has to be equal to the finite element solution, my finite element solution is the correct one. Okay, so this check has to be done element by element, and we should output the values and check. Okay, so this, once this set of tests is done, then we know that at least the part of our element calculation matrix, element matrix coming out of the stiffness only, not the spring part, is correctly done. The load vector calculations are properly done, and the boundary conditions are properly applied. So, if I go up, I can certainly devise variants to these problems. See, one can play around with the boundary condition that one applies. So, imagine I can also do this, I can do this, I can apply the spring boundary conditions, I can do various things to essentially get the effect of the various boundary conditions, and for these various boundary conditions only these coefficients C1 and C2 are going to change. The nature of the solution is not going to change. So, I can play with all the boundary conditions that we have there and check whether my boundary conditions are being properly applied or not. So, all the parts of my program are checked. Solver is also checked, boundary condition application is checked, and also the part where we are outputting the values of the solutions at the nodes. So, the post processor to a certain extent is also checked. Okay. Now, let us go to another set of problems. So, I will call this problem 5. So, here I can have a P, here I can have an F, and I am putting this distributed spring support, spring constant K naught. So, let F be 1, let us assume. So, in this case, what happens to the exact solution? In this case, my differential equation looks like this: minus u double prime plus K naught u is equal to F. Okay. So, in this case, u of x will turn out to be plus C1 e to the power of root K naught x plus C2 e to the power of minus root K naught x. So, let us say we choose K naught equal to 10. Okay. So, we see that in this case the solution is not a polynomial, the exact solution is not a polynomial, but it is rather in terms of the exponentials, or I can write it in terms of cos hyperbolic and the sine hyperbolic functions. Okay. So in this case, I expect that using linear, quadratic or cubic approximations, I should not be able to exactly capture this function, but we should be able to do a good enough job, okay, be close to it. In this case, what should we observe? So what is it that we observe? In this problem, problem 5, as well as in, I would also talk of problems 4 and 5. So in problems 4, you note that if I am using this 3 element mesh, then at these points xi, which are my global nodes, okay, at these points the finite element solution is equal to the exact solution. So at xi is equal to xi. Okay. At other points you may be close, but you will never be exact. For problem 5, this is true for all orders of approximations 1, 2, 3, so on. For problem 5, we observe that if you take these nodes, okay, at xi, UFE at xi is not equal to u exact at xi, but it is sufficiently close. And this how close improves or becomes better and better as the p is raised. Okay. So can we say the reason why this is going to be like this? Why not something else? Can we say that, okay, if I am using a quadratic approximation, okay, what can be said about these points? Why should the solution not be the same as the exact one at these points? Okay, in the general case, for problem 4, for example, okay, this can be given in a very simple-minded way. Let's take the problem corresponding to the node xi. So we have the mesh, we have the node xi. At this node, we apply a point load equal to size 1. And remember, here we have fixed. Let's take the problem as it is. Here there is no end force. So I am simply applying a force in the middle. So in this case, we know how to solve this problem. In this case, the problem would be, the solution would be a piecewise linear. Let's call this solution G, okay, G of x. So this solution is a piecewise linear. Now my question is, as we had discussed earlier, by putting a node here, by having a mesh, should I be able to represent this exactly using my finite element solution or not? Answer is yes. So this will be equal to the finite element solution. So if I took this problem, solved it using the finite element method, okay, this would give me, the finite element solution would give me exactly the solution to this problem. So let's call it by GFE. From what we had done earlier, we know in terms of the bilinear forms that Bu comma V is equal to Fv. So I am simply recapping for all admissible V's. So V is admissible. Now we know what we mean by admissible, that V at the point where the geometric condition is given is 0. Similarly, we also know that if it is true, this is for the exact solution for any problem, if this is true for a V, for any V, then it should also be true for so-called V finite element. and by V finite element we understand that I can write V in terms of my basis functions that are used in the approximation. Okay. So, this is going to be true. Further, I will also have the finite element solution. How are we obtaining it? U finite element, V finite element is equal to V finite element. Now, from these two equations, we can get B U minus UFE comma VFE is equal to 0. This quantity is called the error E. So, this says that the error in the finite element solution is supposed to be orthogonal to all functions which can be represented using the basis functions that were used to form the finite element solution. So, if this is true, then we can talk of the strain energy of U minus UFE is equal to half of B U minus UFE comma U minus UFE, and using what we have obtained here, this will be equal to half of B U comma U minus B UFE UFE. Okay. So, this is equal to strain energy of U minus strain energy of UFE, and this we had said that implies strain energy of U is greater than equal to strain energy of UFE, because the strain energy is positive. So, strain energy of this itself is greater than equal to 0. Strain energy of the error is greater than equal to 0. So, this has to be greater than this. Now, this as yet has no connection to what we have done. Okay. Now, from here, if I have this relationship, let us come back here. Go back to our previous problem. Yes, if we come back to our previous problem here, then if I take this problem, this load, okay, then for this, if I take B of U comma G will be equal to, if you work it out, it will be equal to P1 into U at the point x is equal to xi. This is nothing but the unit load method that you have done. So, what this says is that the strain energy, that is the work done by your existing state of stress against the strain due to this G, okay, is equal to the work done by the applied force against the existing displacement. This is the unit load method that we have done in class, in the mechanics class. This is going to be equal to U at the point x is equal to xi. Okay. But I know that this G is GFE. So, further if I do it like this, U FE comma G okay. Then if I take the difference of the two things, I will get implies B U minus UFE comma G is equal to U at the point xi at the node xi minus UFE at the node xi. But this G can be replaced by the GFE, and using the orthogonality of the error, because this is the error, this side is equal to 0, which means that this difference is equal to 0, which means that the finite element solution at the node is equal to the exact solution at the node. Okay. Now what happens for any other point? So if I have any other point which is not a node, let's take this point. So if at this point I apply a unit load, okay, then the exact solution to this problem will be like this. Okay. Now this exact solution I cannot capture exactly using the basis that we have defined, because my finite element solution can do only this and so on. Okay. So it will not be able to capture this kink. So if it is not able to capture this kink, I cannot say that GFE is equal to G. So if I can't say that GFE is equal to G, then I cannot use the orthogonality property, and I cannot say that U is equal to UFE at any other points. Okay. Similarly, if I take problem 5, the class of problems corresponding to problem 5. So if I have this guy here with these springs applied, put, now I take a node, and at that node I apply a point load P1 equal to 1. In this case, the solution to this problem, G is going to be essentially an hyperbolic cos hyperbolic and sine hyperbolic. Okay. So the solution will be in terms of e to the power of k naught x and e to the power minus k naught x piecewise. Okay. So certainly G, I cannot represent G with the finite element representation in any case. Using p equal to 1, 2 or 3, I cannot exactly represent the G with GFE. So if I can't do it, then even for a node, in this case, in the case of, so even for a node, if this point where I am applying it is a node, that is an end of a element, in that case, even in that case, this condition cannot be satisfied, which means that I cannot use the orthogonality of the error, and so U at the node is not going to be equal to the UFE at the node. This is contrary to what is generally assumed or given as a heuristic proof in the normal finite element literature. Okay, so these values are not going to be exact. Further, even if I don't have the spring and I have a tapered member, in this case also you will see that is not equal to UFE at the nodes, but they are sufficiently close. Okay. Next is, if I go back to what I had done here, if I look at this, this also gives us a way of checking what is happening. Okay. I know that my finite element solution has been obtained. How do I see that if I refine the mesh further, or I keep on increasing the P, I am doing the right thing, that is I am converging to the exact solution, that is through this. So here in the case, we know that U of UFE is less than equal to U of U exact. So what we say, that the finite element solution reaches or tends to U exact from below in terms of the strain energy. So if I am able to compute the strain energy of the finite element solution, then if I take the sequence of the meshes, that is I take a mesh which is a crude mesh, maybe this one, then I refine the mesh, then I take the sequence of finite element solutions, I should get that the the strain energy for the crudest mesh is lesser than the strain energy for the next refined mesh is lesser than the strain energy for the next refined mesh. So this is what we should be able to observe. Okay. So this is always going to be true provided, this is true provided my exact solution at is set to 0 at Dirichlet boundaries. So for the case where I have a Dirichlet boundary condition, there I have to have the case that u is 0. If u is not equal to 0, then this is not going to be true. Okay. So this is a check of what is happening with my approximation. So I should be able to get this monotonically converging to a higher number. Okay. So if I plot for the various meshes, I should get like this, convergence to the exact u from below. Now how do I compute UFE? So UFE, if I see the strain energy of the finite element solution is half of B UFE comma UFE. Okay. But I know that UFE is a choice for a V. So this is certainly going to be equal to half of f of UFE. Okay. This is going to be equal to half of my displacement vector multiplied by the load vector. So I solved for the u transpose, somehow I store the load vector, then this is load vector after applying all the boundary conditions, then u transpose f should give me what is the strain energy. Okay. So this is very easy to compute, and for the sequence of meshes I should be able to check. Another thing that we should be able to check for problems 4 and 5, if I plot, I take this quantity log of, so I will call this quantity I is equal to log of doesn't matter okay. So this I can essentially plot versus log of h. So if I plot this quantity, so what does it say? It is the strain energy of the error, square root of the strain energy divided by the square root of the strain energy of the displacement, log of that I take, this I call as I, then I should be able to see something very interesting when I plot. So I plot here as minus I minus log of h. So I will get for p equal to 1 one curve, for p equal to 2 another curve, and for p equal to 3, and this will be p equal to 1, p equal to 2, p equal to 3, and the slope here, slope will be 1, slope here will be 2, slope here will be 3. So now if I fix p to some value 1, 2 or 3, and then I choose my any LEM, that is the total number of elements is equal to 2, 4, 8, 16 and so on, all multiples of 2, then I essentially get h is equal to 1 by 2, 1 by 4, 1 by 8, 1 by 16 and so on. So if I take the sequence of meshes, these are more and more refined meshes, find for this P the solution, finite element solution. From there I find the strain energy of the error. Remember how we have given the strain energy of the error from our previous slide? It is given in terms of the differences of the strain energies of the exact solution and the finite element solution. Strain energy of the exact solution we can compute explicitly using the integrals. Okay. So, I can do this, find the strain energy of the error and then find the relative error and plot these three things. Okay. For these values I should get curves like this. So, if you can get this, again it is a good proof that your program is doing what it should be doing. That is, we are seeing a ch to the power of p rate of convergence in the square root of the strain energy of the error, which we had talked about earlier. That is, with the h, that is, as the mesh is refined, I get the strain energy of the error, square root of that converges as ch to the power of p. This quantity is called the energy norm. Okay. So, with this I think we have essentially understood most of what we needed to understand as far as this one dimensional problem is concerned. Okay, let us in closing look at some alternate formulations. That is, that we had done, if you remember, either the minimization of the total potential energy of a functional from where we got the variational formulation, or we started with the residue, that is my differential equation. If I take this quantity, I will call it r of x. In the actual, if you use a true solution to the problem, r of x has to be equal to 0. Okay. So, this I had called as the residue. So, what we had done, multiplied this residue with w and integrated by parts once to transfer derivative from u to the w, and we got our weak formulation. What if we simply take integral x is equal to 0 to L of r of x into the weight function w dx. Now, here if I leave it like this, okay, this has to be equal to 0 for our actual problem. So, here this r of x now comes due to a choice of some series representation of u. So, we could use some functions. So, we will say u tilde is an approximation, I is equal to 1 to some n, some alpha I phi to the power phi I of x, where phi I, as we had done earlier, are our basis functions. Okay. So, I put it here. Now, I need to find these alpha i's. I am not doing any integration by parts. So, first of all, my phi i's should be such that u tilde has to now satisfy both the Dirichlet and Neumann conditions. At both the ends. So, now I am asking a little bit more from u tilde, that it has to satisfy the given boundary conditions. Not only that, now the second derivative of u tilde has to be properly defined. So, I should take the phi i's to be sufficiently smooth. Okay. Let us say we have taken them to be polynomials in the whole domain. Okay. Now, I can choose the w of x, because u tilde satisfies all the boundary conditions, w of x need not be constrained by the u. So, u I can choose it to be some sigma I equal to 1 to n of beta I psi I of x, where the functions psi I of x are not the same as the functions phi I of x. Okay. So, when psi I of x is not equal to phi I of x, this is a method. We can do it like this, provided that we have chosen the psi i's in such a way that we get n linearly independent equations in terms of the unknowns alpha I. So if I can get these equations, then I can invert the matrix that comes. You see, this will also lead to a matrix problem in terms of the unknowns alpha I. Solve this and we get a solution. This method is called the Petrov-Galerkin method. In case I use psi I equal to phi I, okay, it becomes the Galerkin method. And in fact, we can do the integration by parts and get the weak form, and we saw that whatever we have done is essentially using this Galerkin. Another way of doing this, which is quite popular in fluid mechanics computations, is I say that I will define a functional j dx. Okay. Now again I choose u tilde is equal to sigma I is equal to 1 to n alpha I phi I, such that the phi i's satisfy all the given boundary conditions, all the given boundary conditions. Okay. So then I am looking for those alpha i's which minimize j. I.e., we want the partial derivative of j with respect to alpha I to be equal to 0, I going from 1 to n. Okay. So now I have, in terms of the alpha i's, n such equations. If I go back and look at the Petrov-Galerkin, here for I and j, if I replace I with j, I need not get the same entry. See, here also I will have some k into alpha is equal to f, but the kij will not be equal to kji, need not necessarily be equal to kji. So this matrix is going to be unsymmetric, okay, and that comes with its own set of problems. If I do things like this here, then del j del alpha I will give me integral x is equal to 0 to L r of x into, if I go to the r that we have taken, minus d dx of Ea d phi I dx. This is equal to 0. So r of x, which has the u tilde sitting there, into minus d dx of Ea d phi I dx. This is nothing but the derivative of r of x with respect to alpha I. Okay. So this is equal to this whole thing, r of x into dr d alpha I. Okay. So this has to be equal to 0. Now you see that in r of x, I will be having r of x as minus d dx of Ea du tilde dx minus f. Okay. So now if I substitute for u tilde in terms of the series, then again I get, and I set up the problem like this, I will get k symmetric, which is something we often desire. Okay. This is called, this whole approach is called the method of least squares. So there are various other alternatives that we can have. For example, the collocation method and so on, where collocation means that W is chosen as a Dirac delta. We are not going to talk about that here. Okay. So we have various approaches to getting our system of equations, provided we have made our series representation for u. That's the crux of the whole thing. Okay. How we get the system of equations is our choice. Okay, and depending on the problem at hand, we will use one way or the other way. Okay, in the next class, in the next lecture, we are going to talk about essentially an extension of the 1D problem to look at a different class of 1D problems, essentially what we know as the beam problems. Why we are going to look at the beams? Because the beam problem corresponding to the Euler-Bernoulli beam theory leads to a fourth order differential equation. So if we have a fourth order differential equation, do we continue with what we have done, or we have to make certain modifications in the structure of things that we have done, okay, in order to handle this problem? That is what we are going to focus on. We are going to look at the beam problem, essentially talk of additions to the program that we have written, the one-dimensional program, in order to handle the beam problem, and we will go from there. Thank you.